Hello everyone, welcome. We're going to do a summary of chapter 6 to help you prepare for the test next week. Over here I have a list of everything that you are supposed to learn in this chapter, so we'll go through them one by one. I can already cross out this part because 6.4 will not be part of the test. Okay, so the chapter is about heat, and heat is a form of energy, and it is measured in either the unit joules or in kilowatt hour. These are both units of energy, just like you can measure distance in meters or, for example, miles. Heat is closely related to temperature, but they are not the same. The example that we looked at was that when I try to, for example, melt ice, then the temperature of the ice will stay the same during melting, but I'm still supplying heat if I'm melting it, for example, by putting it in a pan and then putting it on a stove. Then the stove will keep providing energy, but the temperature will not change. So these two things, they are not the same. Heat is energy, temperature is more of a measure for the movement of the molecules. The faster they are moving, the higher the temperature. Part of the goal was to find out how exactly these two are related mathematically, and therefore we first have to look a little bit more at heat by itself. The heat supplied by an electric heater depends on two things: the power, and power equals energy per second. Energy per time, I should say. So the unit of power is the watt, which is the same as the unit of energy, joules, divided by the unit of time, seconds. So it's often given in joules per second. It also depends on time, of course. The longer you use a device, the more energy it will use. Now, time is most of the time given in seconds, and to see what unit that will give for heat, I can look at power. If I take this formula, heat, for which we use the symbol Q, equals power times time. Then I'm multiplying something with the unit joule per second by time, which is in seconds. So when I multiply these, the seconds cross out and I am left with the unit of joules. This could also be done in a different unit. Power can also be given in watts, we have already seen that, or even in kilowatts. And kilowatts and watts relate to each other the same way meters and kilometers do. And the time in hours. If I multiply kilowatts by hours, I get the other unit, kilowatt hour. So this is simply another unit that we can use. So this tells you how to calculate the provided heat with if you have a device that uses a certain power. To calculate power, you sometimes need this formula from the previous chapter. Power equals U times I, voltage times current, with voltage given in volts and current given in amps. Okay. this basically covers the first paragraph of the booklet. Now let's remove this and we're going to see how heat and temperature relate. They relate to each other by this formula. Heat equals mass times specific heat capacity times temperature difference. For this formula, heat needs to be given in joule, the mass needs to be given in grams, temperature needs to be given in degrees Celsius, and that leaves the unit joules per gram per degree Celsius for specific heat capacity. Sometimes it's also written down like this: gram to the power of -1 and degrees Celsius to the power of -1. As you may know from mathematics, 1 over x equals x to the power of -1. So these two are actually the same. The specific heat capacity is a number specific for a certain substance. For example, the specific heat capacity for water equals 4.2 joules per gram per degree Celsius, which basically means to heat 1 gram of water by 1 degree Celsius you need 4.2 joules. You don't need to learn these numbers by heart. You will be given a table that allows you to look up these different heat capacities. So if you know that, and you know, for example, how much water you have, how much it weighs, and you know how much you want to heat it, to what temperature, you can calculate how much energy that takes. Do be careful that you cannot just heat water above, for example, boiling temperature. Water solidifies at 0 degrees Celsius and boils at 100 degrees Celsius. So if you want to heat water to 110 degrees, for example, you first need to boil it away, and that takes a lot more energy. So in that case, you cannot use this formula. That sums up paragraph 6.2. Then, heat transfer. When I bring two substances into contact, then they will start to transfer heat to each other. This works very simple. If I have two objects that are in contact and they have different temperatures, but for example this one has 10 degrees Celsius and this one has 20 degrees Celsius, then heat will flow from the warm object to the cold one. And this will continue until both objects have the same temperature. So when, for example, this one is 15 degrees Celsius and this one is also 15 degrees Celsius, heat transfer will stop. Now this works because I've assumed that these are two blocks of the same mass and the same material, so they have the same heat capacity and there's no heat going to the surroundings. And that of course is rarely completely true. But to be able to do any calculations, we often need to do some assumptions. So, for example, when I mix two substances, water and oil for example, I will often assume there's no heat going to the surroundings. Of course, when I mix two substances, they might not have the same mass, and if there are different substances, they will not have the same heat capacity. But what is still true, that the warm object will lose heat, Q lost, and the cold object will gain heat, Q gained. And these two will be equal to each other, because if the warm substance loses 200 joules, then the cold object will gain 200 joules. This allows me to find out stuff about these substances, because I can replace these formulas by the formula Cm times delta T. And I can do the same on the other side. I'm using labels to keep track, because the temperature difference for the hot object will be different from the temperature difference for the cold object. These are not necessarily the same numbers. So by using labels, I can keep track of them and not confuse them. And so, for example, if I know all numbers but the specific heat capacity of the cold object, then I can calculate it from this equation. If you want to look at specific examples of this, please look up the other explanation videos. But this is basically what it means. So that concludes the third paragraph. Good luck to you all studying, and I will see you all in class.